I'm Glen Bertini, and I am author of the paper, The Molecular Thermodynamics of Water in Direct Buried Power Cables. The paper was published in IEEE's Electrical Installation magazine in the November-December 2006 issue. I know the title is a mouthful, but the content is actually quite simple. The paper answers several interesting questions, but in this video, we are going to look at answering just two. 1. How much water is there at the depth at which direct buried primary distribution cables are installed? And 2. What is the implication of the presence of that water? The paper answers these two questions and many more. I would encourage you to read the entire paper at the Novinium website. This map shows the amount of water represented as millimeters of water in the top 2 meters of the soil column for the conterminous 48 United States. Dark green means lots of water, lighter green means less water. If your cables are in Canada, you have to extrapolate from your border with the US. Cables are generally buried about 1 meter deep. Right now, we are looking at 30-year averages from 1961 to 1990 during the month of January. As we watch the 12 months advance from January, we see that the amount of water varies depending on where your cables are buried. In North America, the driest portion of the year, where the soil water content is at a minimum, occurs in August. As we progress further into the fall and winter, wet weather quickly replenishes the water lost from the dry summer months. As you watch this progression, you might have noticed that even in the driest month of August, which we return to now, there is almost at least 100 millimeters of water in the top 2 meters of the soil. Most of the soil in most of North America is wet most of the time, and that doesn't even account for landscaping irrigation, prevalent where most underground residential distribution cables are buried. Here's the part that trips up many people. Air at 100% relative humidity is no different than liquid water as far as the cable is concerned. To understand why this is so, let me introduce you to the concept of fugacity. Fugacity is the chemical potential of a material. At equilibrium, that is, given long times with stable temperatures, the fugacity of a liquid or vapor is the same in adjacent phases. The amount of water in the soil and the temperature of the soil at 1 meter of depth is very stable, so actual fugacity values are very close to equilibrium most of the time. The fugacity of water molecules within water droplets trapped between grains of sand is the same as the fugacity of water vapor in the airspace between those same grains of sand, is the same as the fugacity of water present in the insulation shield, is the same as the fugacity of water present in the insulation, is the same as the fugacity of water present in the conductor shield, is the same as the fugacity of the water vapor present in the strand interstices. If the equilibrium is perturbed, water permeates from high fugacity to low fugacity. If the soil is wet, and it almost always is in the thermodynamic sense, the cable is wet. The growth of water trees, the predominant cause of cable failures, proceeds at the same rate whether the cable is immersed in a pool of water or buried in typical North American soils at 1 meter in depth. There are many more gems to be found in the off-cited Molecular Thermodynamics of Water in Power Cables paper. Check it out at Novinium, Masters of Reliability website.